This video covers material about chemical bonds, the basic reasoning behind the concept, and how are these formed. The material presented was originally developed by Jianhui Fang and modified and narrated by Alan Rodriguez. This video is made possible by the National Science Foundation funded project Boat of Knowledge in the Science Classroom at Ohio University. So let's start. The first question I'll make to you is, do you know what is the building block of all matter? Furthermore, do you know what is this building block made of, or what are its components? Is this block always alone in nature, or does it present itself with a lot of neighbors? If it's not alone, then how does it remain binded or connected to its neighbors? If you answer no to any of these questions, or even if you feel you should review these concepts, then I invite you to study and review with me the presentation titled Chemical Bonds. In order for me to introduce this concept briefly, let's start by first going into the most simple form of a complete component of matter. This answers our first question that stated, what is the building block of all matter? Do you know? Well, I'll tell you. The building block of all matter is an atom. So here's a model of how an atom looks like. Let's answer our second question that stated, what are the components of the basic building block? Briefly reviewing, in the center of the atom we find protons and neutrons. Protons have positive charges while neutrons don't have charge, they're neutral. In the outer part of the nucleus, which is composed by neutrons and protons, we find what chemists call shells or orbital types. In these orbitals, we find the electrons, which have negative charges. Now, for our study, we'll be focusing on the electrons of the atoms and how the distribution of electrons will help determine how many chemical bonds an atom can make and how can it make it. So remember we spoke that the atoms have orbitals or shells. So as you can see here, these shells or orbitals are distributed according to the area of the periodic table at which you're standing on. Besides the orbitals or shells, there are also levels. The higher the level, the further the electron shell is from the nucleus. It's important to mention that the actual name of these levels is energy levels. As you can see in the picture, the shells are named as S, P, D, F. In the picture, they are distributed by colors and sections, and the numbers next to these letters represent the energy level at which you are standing on. In each shell or orbital, a specific amount of electrons can be located. In orbital S, only 2 electrons can be located. In orbital P, only 6 electrons. In orbital D, 10 electrons, and in orbital F, 14 electrons. Note that per each box, 2 electrons can be located. When you determine the energy levels and the orbitals with the electrons in each level for a specific atom, you got to write what is known as the electronic configuration. Now let's go ahead and apply this principle to the atom F, which stands for fluorine. So let's first locate fluorine. If you want, pause the video at this moment and find a periodic table so that we can go in this together, as the periodic table that I'm showing might be difficult to follow along. So this is fluorine. Now, this is our periodic table, and the periodic table showing the orbitals and how many electrons fit in each orbital. So before fluorine, we find helium and hydrogen in the first energy level. I'm showing these atoms and the energy levels with the arrows above. So because these 2 atoms are before fluorine, it means that the first energy level, 1s with the orbital s, it's full, or it has 2 electrons. So orbital S in the first energy level, it's full. So let's move down. In the second energy level, we find lithium and beryllium. Here, these two atoms are also before fluorine. So because they're before, it means that fluorine has the electrons of these two. So that means that the second energy level in the orbital S is full of electrons as well. Now if we move to the next side of the second energy level, or the green side, we find the orbitals p in the second energy level. Now we see that right before fluorine, we find boron, carbon, nitrogen, oxygen, and then fluorine, which means that out of 6 electrons that this orbital has in the second energy level, corresponding to boron, carbon, nitrogen, oxygen, fluorine, and neon, fluorine is before neon. It means it's missing 1. So the orbital p in the second energy level is not full. It has 5 out of 6 electrons. So because it has 5, now we can write the electronic configuration for this atom, which looks like this: 1s2, 2s2, 2p5. Now, because in 2p 6 electrons can be located, however, fluorine has 5, the question is, what does fluorine do to fill that empty space? Well, that's where chemical bonds take a role. Now, let me ask you a question. Who do you think is more stable? An atom with the whole shell or orbital full, or an atom with the orbital not full? If you answer an atom with the orbital full, you are correct. Noble gases, or the atoms found in the last right column, as I'm showing here, have their last energy level and orbital full, meaning that they are stable. So all of the atoms in between will look, or will like to look like them, or have their orbital full of electrons in order to be stable like them. So going back to our previous slide, you notice that the electrons in energy level 1 of fluorine are complete, and the atom has another energy level, in this case is 2, at which electrons are found. These electrons are the ones available to react to form bonds, and these electrons are called valence shell electrons. This means that the valence shell electrons are the ones that are on the highest energy level. So in our example of fluorine, we determined that the orbital p in the energy level 2 is missing 1 electron. Remember that if fluorine wins 1 more electron, it will resemble the electronic configuration of neon, a noble and stable gas. So in this case, fluorine is desperate to have that orbital full. So, can you guess who can be an optimum candidate to supply that missing electron? If you answer hydrogen, you are correct. Hydrogen has only 1 electron in the level 1, or energy level 1, orbital s, which means that if it wins 1 more electron, then it can resemble helium, a noble and stable gas, as it has the orbital s full on the first energy level. So it's a win-win situation. If hydrogen bonds to fluorine, fluorine provides the missing atom for hydrogen, and vice versa. This type of bond is known as a covalent bond, or a bond between 2 non-metal atoms. If the bond is between a metal and a non-metal, then the bond is classified as ionic. As you can see here on the bottom picture, hydrogen and fluorine both complete their orbitals, so now hydrogen resembles helium in stability and fluorine resembles neon in stability, and now they're both happy. Now, can you do it? Let's do a small and easy challenge. Try to write the electronic configuration of hydrogen and chlorine and determine if these two can make a bond. if they can determine what type of bond they can make. It is important to mention that what we've covered here is just a really basic concept of what builds and promotes the formation of a chemical bonding. We have not discussed all the types of chemical bonds, nor the insistent electromagnetic interaction and forces considered as chemical bonds. For more in-depth information, I encourage you to study any available general chemistry book or ask to your chemistry teacher about this particular subject. If you're interested, Lewis structure will be a great place to start. Thanks for your attention.